Hi everyone. I'm very excited to introduce Adam today. Adam has some really incredible work in interpretability. Everyone here, like you're absolutely in for a treat. So I'll just let you get started, Adam. Feel free to share your screen and start presenting.
Alrighty. Let's see. Sharing. All right, is the screen sharing working?
Yeah, we can see it.
Okay. Alrighty. Yeah, so the main topic of this talk is a paper I had called Evaluating Sparse Autoencoders with Board Game Models. So I'll start with just like a brief introduction on sparse autoencoders. So we use sparse autoencoders to understand neural networks and interpret them. But one question is, why do we use sparse autoencoders? And there was some like early work looking at like fairly natural units to decompose the neural network. One is the MLP neurons contained in the network. And there was some success, but there was this issue called polysemanticity where neurons typically corresponded to multiple concepts, and this made it challenging to interpret what was going on. And this problem just got way worse with LLMs. And probably the basic problem here is just that there's more concepts that exist on the internet than there are neurons in the network. If there's on the order of say 100,000 neurons in the network, well, there's just way more concepts on the internet. If you just think about the birthplace of every celebrity, et cetera. So an example neuron might correspond to like, this is an example one from an Anthropic paper where it corresponded to academic citations, English dialogue, HTTP requests, and Korean text. So we need some way to like decompose what's going on in the model. First, to introduce an autoencoder. Basically, autoencoder just takes vectors as input and it tries to reconstruct them, but it compresses the vector, which makes the task challenging, so the reconstruction isn't perfect. So in this case, the input is just a four-dimensional vector, which just means a list of four numbers, and the autoencoder tries to compress this to two numbers and then expand it back to four, matching the original input. So sparse autoencoder is a pretty related idea. Except instead of trying to compress it into a smaller dimension or a shorter list of numbers, we instead have a much larger hidden dimension, which this would be trivial, except that we impose some sort of sparsity constraint where we only want a few of the numbers in the hidden activations to be non-zero. So in practice, we have like a fixed width vector in the hidden space, and you can kind of think of every one of the dimensions of this vector as like a variable. So the width of this is a hyperparameter that we choose. So if the width is 2000, then that means you have to reconstruct the model activations using, say, only 20 of these 2000 variables. And interestingly, this sparse autoencoder is inspired by the sparse coding hypothesis from neuroscience. So I'll go into a little more detail here. It turns out this is extremely simple. The encoder is just a matrix. It's just a matrix multiply, a single layer. And we apply, in the simplest form, we just apply a ReLU, which zeroes out most of the values. Another matrix multiply with the decoder. Now we have the reconstruction. So typically, when training, we could just have a loss function that incentivizes sparsity in the hidden activations, or we could like another approach is to zero all but the top k activations. So in this case, if k equals 2, we zero out everything except for the top 2 activations. And maybe for additional intuition, this is like basically the exact same thing as a MLP layer in a LLM. with the difference that we don't have the MLP layer does not have a sparsity constraint, and here we do for a sparse autoencoder. And the MLP in an LLM typically has an expansion factor of around 4, where in a sparse autoencoder, sometimes our expansion factor will be like 100x. So in this case, these red boxes are just a single feature in the sparse autoencoder. So this is it looks like a 8-dimensional sparse autoencoder. So we have, you can think that basically we have the sparse autoencoder has 8 variables to work with. And for any given activation, it has to reconstruct the input using only 2 of these variables, where it can apply, it can apply weights to these, but it can only use 2 of them at any one time. So we're trying, the way I think of a sparse autoencoder is just a unsupervised decomposition of model activations, where model activations is just like a dense vector. There's a bunch of numbers. You have no idea what's going on. And with the sparse autoencoder, we decompose it into a sum of just a few different variables or features. And hopefully these features are interpretable. And typically how we interpret the features is basically we just look at what text makes this feature activate, where the feature is just a single dimension in the hidden space. So this is a sycophantic praise feature where if you look, whenever it's activating strongly, it's activating on some sort of sycophancy, where this is not like a very like surface level thing that can just be gleaned from the tokens or something. The model has to do something more abstract here to come up with this sycophancy feature. And then we can take we can also take this feature and steer the model, and this makes the model behave as a very sycophantic assistant. So this gives us like additional confidence that we know what the feature is doing. And just, I'm not going to go into detail here, but just showing that sparse autoencoders are just actually extremely simple. You can implement the entire thing in like a handful of lines of code. And when we perform interventions with the sparse autoencoder, all that we are doing is we are indexing into the decoder matrix, which is just a number of features by D-model matrix. We just grab one of the vectors and we add it to the residual, or we add it to the model's activations before sending it through the rest of the model. So a lot of sparse autoencoders work and interpretability work is really actually pretty simple. So that was the introduction to sparse autoencoders. Now, one of the motivations for our paper is that there's just been a ton of interest in sparse autoencoders. There's been, I'm aware of at least a dozen new approaches that have been proposed within the last year. Some of these have also been rediscovered because sparse autoencoders were like originally introduced over 10 years ago. So some of this has just been rediscovering, older approaches. For example, the top case sparse autoencoder is an old approach. But a real problem the field has is we just didn't have a good way to determine which one of these is best. So if we evaluate a sparse autoencoder, one common way is using these unsupervised proxy metrics. So the simplest metric is if at a fixed level of sparsity, how well does it reconstruct the model activations? Where this is like the fidelity of the reconstruction, which this is like a decently intuitively compelling number, but it doesn't really correspond to what we want, which is like a interpretable decomposition of model activations. And we found that, for example, Anthropic found that some loss functions that improve on this unsupervised proxy metric actually make for less interpretable features. So it's not the only thing we want. Like another common strategy was just manually inspecting the features. This is just like a vibe check for like, does this autoencoder have interpretable features? This is like obviously not an ideal metric. And there was also some like weakly supervised metrics. For example, Anthropic did one where they just take all the elements from the periodic table and they see, does the sparse autoencoder have a feature for every one of the elements in the periodic table? Where this is interesting, but the challenge is like this is just impossible to do for all the different concepts available in on the internet. So in this paper, we instead looked at board games of Chess and Othello, where unlike natural language, there's a few advantages. So like there's an explicit measurable board state, and we can easily enumerate everything that there should be, like all the different pieces, all the different squares, etc. And the board states are always objective. There's no subjectivity involved. So we had worked with a couple of models, ChessGPT and OthelloGPT. And these models are just trained to, just like an LLM, they're trained to predict the next character. So the only difference is their training data set. So ChessGPT is trained on transcripts of real chess games. OthelloGPT is trained on transcripts of randomly generated Othello games. And basically at any character in a given PGN string, which this is a PGN string, just like a way of writing down the moves in the chess game. And at any character, there's like a underlying board state that we can easily extract. And this is what we use as our data when we're evaluating our sparse autoencoders. So in the paper, we, like the most basic thing to do is to just, look at like, is there a white knight on F3? Is there a black pawn on this square? But we also looked at chess has much more interesting properties. And in ChessGPT, I'd found that a very small chess model, like 25 million parameters, trained on chess games, it actually learns much more interesting, like high-level strategic aspects of the game. For example, it is pretty good at estimating the skill level of the players that are involved. So we also look at some higher level strategic concepts, such as, are there any pinned pieces on the board? Is there an en passant capture available? Am I in check, etc. And then we use some techniques to, because we can automatically measure these board state properties, we just develop some techniques to automatically find features that are connected to the board state properties. And here's just like a neat, interesting example of a feature we found that corresponds to en passant, where you can see in this PGN string at the bottom, it only activates twice. And in each instance where it activates, white happens to have an en passant capture available. And then as soon as the en passant capture is no longer available, the feature turns off. So this is especially interesting because ChessGPT is just trained to predict the next token. It's never given any rules about the game or any strategic concepts. It just has to like learn this in order to predict the next character. And then sparse autoencoders are also trained on a purely unsupervised objective of just reconstructing model activations with like a sparse sum of these internal variables. And it turns out that it finds very interpretable variables corresponding to high-level concepts, such as an en passant capture is available. So the first contribution from our paper were these board game metrics. So we developed two metrics in this paper. The first was called coverage. And this is basically, if we have these list of, we have this list of board state properties, and for each property, such as, is there a black knight on F3, we just see, is there a feature in the sparse autoencoder that is highly aligned with this board state property, where this feature can be an accurate classifier for if this property is present. And then secondly, we had this board reconstruction metric. And the question we asked here was, how well can we reconstruct the board only given sparse autoencoder features? And I think this is an especially interesting aspect of working with board game models because, for example, with the coverage metric, we can do analogous things in natural language. We can be like, is there a feature for all the elements in the periodic table? Is there a feature for, concepts like profession or gender? But there's no way we can like explicitly measure if we can like completely reconstruct the underlying state of the world when the model is generating text. But with board games, we can. So this just shows how the coverage metric works. Basically, for every board state property, we just find which SAE feature has the maxed F1 score at classifying if this property is present. And for each property, we just select the max F1 score. So this should be like a fairly familiar metric. We like do it all at once in parallel, so it's fast and cheap to compute. The board reconstruction metric is a bit more complicated, a bit more unusual. And maybe as motivation, there had been some work looking at OthelloGPT under the assumption that for any given fact about the board, such as in Othello, there's not like white pawns. There's only it's kind of like Go. There's only stones. There's white stones, black stones, and blank squares. And some people had looked at Othello with the assumption that, for example, there should be a single feature that accurately classifies there's a white stone on square A4, and they'd found that this is not in fact the case. So we instead operated on a separate assumption that we won't have features that conveniently correspond to single concepts, but we will have features that are high precision classifiers for some fact about the board. And we also don't impose an assumption that these features should correspond to only a single piece. We allow them to correspond to multiple pieces at once. And we did have some inspiration, like, for example, studies have been done on really good chess players where if you give them a bunch of random pieces on a chessboard, they are unable to like just glance at the board and memorize where all the pieces are. But if you take a chessboard from a real game, they can glance at the board and memorize the state of the board and reconstruct the state of the board, which indicates that they're not just like memorizing the location of every individual piece, but they're instead aggregating patterns somehow. So our first step was just for every feature, we find if it's a high precision classifier for any facts about the board. So for example, some features will be high precision for no facts about the board. Some might be high precision for there's a white pawn on B6. Some might be high precision for multiple pieces. And then once we have identified these features, we take an unseen test set and we see how well we can reconstruct the board state based only on our feature activations and the labels we have for our features. So in this case, you can see we've correctly identified 4 of the pieces. We've correctly identified 4 of the pieces. We have a false positive here with a black bishop, and we have a false negative as well. So here we've correctly classified 4 out of the 6 pieces. And then we just compare our reconstruction with the ground truth and get an F1 score. And we ignore the blank squares because they might be too easy. So those were our 2 metrics. We had a second contribution, which is p-annealing. And basically the idea is at the time, another fact about sparse autoencoders is, because it's such a new field, it moves incredibly quickly where actually, this paper is only 6 to 9 months old and already a decent amount of it is a bit out of date. But at the time we were doing the paper, probably the dominant way of training a sparse autoencoder was using L1 sparsity penalty. So this is basically the sparsity penalty is the sum of the hidden activations. And that looks like this square here. But we evaluate our sparse autoencoders based on the L0 norm, which just measures how many of the values in the activations are non-zero. And basically the idea with p-annealing is just throughout training, we get a better and better approximation of the L0 norm by modifying the sparsity penalty. So I think like a fairly natural idea, we found that you can't immediately start off with the, like a close to the L0 norm because training just falls apart. You have to really start with the L1 penalty and then gradually anneal throughout training. So we found a few facts here. The first is that the metrics that we came up with are board state property metrics. They seem to correlate with SAE quality. So there was this general sense or superstition or like qualitative finding that the best SAEs were somewhere in the range of like 20 to 200. And in this graph, the very top left is the target where we want a very accurate reconstruction on the y-axis with a very low sparsity, a very low L0 or a very high sparsity on the x-axis. So we can see that the dots on the graph that are closest to the top left generally also score the best on our supervised metrics, which is interesting because, maybe if you had to make a guess or a bet going in, you would have thought that, oh, these metrics should be hackable by just having a higher L0 or a lower sparsity. So this graph is two things. The color shows our supervised metrics, and the XY position shows the trade-off between sparsity and reconstruction fidelity. So this has been the primary metric that the field has worked on, where basically you just want to see that if you examine multiple sparsity values, you move closer to the top left of the graph. So we evaluated, this is the standard ReLU approach with the diamonds. We can see it does the worst. A gated SAE was like a concurrent improvement that we evaluated. We also have our p-annealing approach, and p-annealing can stack with the gated SAE. So if we look at these three improvements based on the standard proxy metrics, we can't really tell them apart. Looks like there's a question.
Apologies if you're like going to cover this in the next slide, but when you see these, this sort of like loss recovery, do you have a complexity for the board state position metrics of like, well, en passant is not something that beginners see all the time, but maybe like the position of a knight is easier to recover or something, or are they kind of all equal in?
No, we evaluated we had separate graphs for low level concepts and high level concepts because there wasn't like a really nice principled way to combine them. Like for example, if you look at all square piece combinations, it would be there's 12 piece types times 64 squares, so I think 768 different combinations versus on the order of a dozen high-level strategic concepts. So we just made separate graphs for them, and we didn't try to consider the relative complexity of any of these concepts either. Yeah. So, anyways, basically using like the standard metrics in the field, we see three different proposed improvements, and they all seem to perform about the same. And we can't really distinguish any of these new proposed improvements, which is challenging if you only have a single metric and you try a bunch of ideas and they all look about the same. Is this because you're reaching some fundamental limit, or is this because your metrics aren't very good? And what we found is that our supervised metrics can distinguish between sparse autoencoder types, even if the traditional existing proxy metrics cannot distinguish between them. And we also found that for several of the metrics, our proposed p-annealing approach actually performed the best. And you can also see that the best values are obtained in the L0 range of like 0 to 100, which corresponded with like existing qualitative findings on where the most interpretable features could be found. You can also see that there's, for most architectures, there's these parallel lines. This is most prominent with the gated SAEs trained with p-annealing. And these parallel lines correspond to sparse autoencoders trained with different, wider and narrower hidden spaces, where this isn't very prominent on the existing proxy metrics, but it's much more apparent under our supervised metrics. So that was the story of the paper. It got accepted to NeurIPS. And I think it was a pretty reasonable story. Is an interesting paper. Now this paper is, on the order of, 8 months old or something. So I have a bit of a retrospective on it. So probably the biggest result is I did follow-up work where we created this benchmark called SAE bench, which is just a benchmark of evaluations for sparse autoencoders. All of the problems I talked about with natural language apply, we don't capture the entire breadth of concepts in the world, but we do have the advantage of we're just directly working on large language models. We're not working this toy setting. There's always a trade-off where toy settings are easier to analyze, but all of the lessons you've learned might not transfer to the real world. And anyways, with SAE bench, we found that there was one proposed approach called the Matryoshka SAE, which performed significantly better on several of our metrics. Here, you can see on this is called the spurious correlation removal metric and the feature absorption metric. It clearly stands out from the crowd. But we also evaluated the Matryoshka SAE on our board game metrics, and we found that it didn't really stand out, especially in the normal L0 range of like 0 to 100. And I think generally myself and other researchers just trust the SAE bench metric more because it's closer to the real world, closer to large language models, even if it doesn't have the advantage of the board game evaluation. So I think that weights me a bit against this board game's work. A second retrospective is that we evaluate p-annealing here in SAE bench, and we find that it doesn't really stand out from the crowd of all of the proposed approaches. It probably will not be adopted. There's several approaches proposed after it that perform better and often have less hyperparameters to tune. However, there has been follow-up work examining board games plus SAEs. I'm aware of at least a couple projects, and I think there's pretty interesting work that can be done here. A lot of work with interpretability in large language models feels very hands-on and empirical. And I think these toy settings can provide more fundamental insights into what's going on. If you view there's some trade-off between toy settings that are easy to understand and real settings that are complicated to understand, I think that board game models may represent a somewhat optimal trade-off if you're really interested in understanding how models work. And I'm aware of some work looking at this that I think could be potentially exciting. Another retrospective thought is that even if our metrics don't end up being super useful, I think it was still pretty useful to know that in general, we were able to reconstruct most of the board. With our board reconstruction metrics, the values obtained were often like 90%, 95%. So this indicates that there's a big concern because a sparse autoencoder does not perfectly reconstruct model activations. There's a pretty big concern like what's in the missing reconstruction? Is this where all the important stuff like, a big motivation behind studying interpretability of neural networks is looking for deception in future super intelligent models. And there's a big concern that we will be applying our interpretability technique to these extremely smart models, and the deception will be hiding in the error term, or other important concepts might be hiding in the missing reconstruction. And in our work, it seems like, well, if we apply like pretty straightforward techniques, it seems like we're actually able to reconstruct the entirety of the board, which seems kind of promising. But, there's always an element of doubt here because this is a toy setting, and there's always a chance that lessons learned don't transfer. So yeah, that's the overview of our paper. I'm happy to take any questions.
Great. Thank you so much for the talk, Adam. Let's everyone, we'll give you a virtual round of applause. Yeah, this is really fantastic and really interesting. If anyone has a question, feel free to unmute, raise your hand, ask in chat, any of the above. I'll go ahead and start us off with a first question. You talked about it a little bit with the context of deception, but like I'm curious if you could just talk a little bit more to the direction you see of this type of interpretability research, and especially like the applications that you foresee it being useful in.
Yeah, there's a pretty common criticism of interpretability and sparse autoencoder research that it hasn't really been useful for anything yet, which I mostly agree with. I think there are some like, somewhat contrived or niche cases where it is useful, but for the most part, I think interpretability hasn't been that useful yet. Maybe this is just like a fundamental limitation of the field. Maybe we're just still early enough. And interpretability just needs some more research time, and we'll get there. I think this is to an extent, like I think machine learning just works extremely well when it has data to optimize against. So in cases of like, I want to steer model behavior, I think if you have examples of your desired output behavior and you can fine tune your model on it or perform RL on this data, or perform RL, in some environment with some verifiable rewards, I think it's just going to be very difficult to use interpretability. I do think, one idea that's kind of tossed around is I think using LLMs is fairly challenging in certain industries, like, for example, maybe medical or banking, because there's concerns about bias. So maybe interpretability provides us a confidence in what these models are doing to, let them be used in past audits. I think another, there's some interesting work out of Anthropic where they do this technique called model dipping, where basically they fine tune on some data and they show these are the features that have changed. Here's the new features that have emerged because of the fine tuning. And they've done some experiments where they take like a normal language model and they fine tune it to, specifically, they do a thing called sleeper agents, where basically when the model sees this tag indicating that's in deployment, it's supposed to tell the user that they hate the user. And I think model dipping with interpretability has been so far one of the most successful techniques to identify the change in the model, even though when interacting with the model normally, it behaves perfectly normally. Like this is just something that's triggered by a secret phrase. Interpretability techniques have been pretty effective at finding that. So this is another direction of research that seems like it might be promising. But yeah, and I've seen, for example, I think some people at Stanford really like to criticize sparse autoencoders because they aren't useful at steering model behavior. But I'm just kind of like, this is the wrong tool for the job. If you really want to steer your model, just like give it a good prompt or fine tune it.
Yeah, that makes sense. Great answer. Let's see. Let's check chat. We have a question from Nathan Bartley. He asks, does the complexity of the game matter in reconstruction? Do you think you'd be able to reconstruct checkers board states better than chess or Go?
We did find that we were better able to reconstruct Othello boards versus chess boards. Off the top of my head, the score was something like we could reconstruct Othello boards with like, say, 95% accuracy, and chess was on the order of 85 to 90%. So this is like a bit of an indication that complexity does matter. But I would say that I think that the techniques we use here were like just really straightforward and simple. And it's interesting that such just extremely simple approaches could work well. But I think there's definitely room to use better techniques to estimate how well we can reconstruct the board. One technique that comes off the top of my head is we just look for features that fired with high precision. And I think instead, maybe what you'd want to do is train linear classifiers for each fact about the board, such as is there a white knight on F3 or something? Train linear classifiers on a sparse number of features, and I would guess an approach in that general direction would probably work much better for reconstructing the board.
That makes sense. I'll ask another question. Do you have any like practical advice for people wanting to implement sparse autoencoders or these linear models? You mentioned hyperparameter tuning being an issue before. Just any general intuition or advice?
Yeah, for practical work, I generally favor the top K autoencoder, or there's another approach called the batch top K autoencoder. The reason is that when training typical sparse autoencoders, you have to set this sparsity penalty. And basically, if I want to obtain a sparse autoencoder with the L0 of 50, which just means that 50 values are non-zero on average in any given activation. I need to do this process of like, guess what the sparsity penalty should be, train it for 30 minutes. Oh, it ended up too high. Now I'm going to try a new training run and set it a bit lower, which is just like a really annoying thing to do. Versus with top K, you just say, I want to take the top 50 features, and it just works. It also seems to be like extremely robust. You never really need to tune hyperparameters. Other approaches like jump ReLU have been known to be a bit finicky. In terms of using it, I think there's a couple popular open source libraries. For example, dictionary learning and SAE lens are two that are pretty popular. Yeah, and I think in particular, crosscoders are a pretty exciting potential new approach. A crosscoder, for example, one thing you can do with a crosscoder is, assuming you have two models that share the same tokenizer, you can basically the input to the sparse autoencoder, you can just concatenate their two activations. And they share the same encoding space. And basically what this means is we can start to find, do these models share the same underlying concepts? For example, if I take a 3 billion parameter model and a 70 billion parameter model, you can see how many how many of the same concepts do these models share? I think this work like this has also been done. For example, if I have a a convolutional neural network and a transformer, and I train them on the same task, do they seem to find the same features? And often what you find is, yeah, they do find very similar features. So I think this is a pretty new and promising direction for interpretability research.
That's super fascinating, and I appreciate you bringing up cross encoders and SAE lens. Excited to look into that more. Any other questions from anyone in the audience? Okay, why don't we call it here then? Adam, again, thank you. This was a fantastic talk, super interesting, super insightful. Thank you for coming to speak to everyone at ISI today.
For sure. Yeah, thanks for having me.
All right, have a great rest of your day, everyone. Thank you so much.
Bye.